Now, we can't talk about energy and enthalpy and thermodynamics without talking a little bit about Hess's Law, which is just kind of a cool way that we can manipulate reactions. And if we don't have all the pieces to the puzzle, if I know kind of the steps that it takes to get there, then I can determine the energy of an overall process. So before we get into the nitty-gritty details of Hess's Law, let's look at what we get from delta H information. So if I have a delta H, in this case of formation, so I'm forming 1 mole of water, and this looks a little bit weird because we hammer into, you guys who are learning chemistry, that we need to have simple whole number ratios for our balanced chemical processes, right? But when I'm doing a heat of formation, right, which we would recognize as a sub F there, and probably under standard conditions. So we would have our degree symbol there that indicates that it's at 25 degrees Celsius and 1 atmosphere of pressure. That it's really the formation of 1 mole of that particular compound, or 1 mole of that substance. So it's whatever it takes, whatever fractions of things that it takes, or whole number things that it takes to get to 1 mole. So it does reduce down. So this is kind of one of those weird exceptions to the balanced chemical equations where we say you can never have fractions except when you can, which is in thermodynamic equations, especially and specifically heat of formation. So what I'm doing is I'm reacting together my component pieces, my elements here in their reference forms to form my water. And it has a specific delta H associated with it. The sign on this tells me whether or not it's endothermic or exothermic. In this case, we would say this reaction is exothermic because it's negative. That means that the heat is being evolved from the system into the surroundings. The second piece of information that we get from this is if I was to do this process in reverse, so if we were kind of calling this a forward reaction, where my reactants form products in kind of a traditional sense, if I was to flip-flop this thing and have my what were products now as reactants and go in the opposite direction, this would be called the reverse reaction as opposed to the forward reaction. We would take the same amount of energy to do that, but I'd have an opposite sign. So because I have an opposite sign, this says I need to put energy in from the surroundings into the system to break apart water into its component elements, into its reference forms. So this is an important piece of information because if I know the reaction in one direction, if I need to rearrange, if I need to manipulate, if I need to add things together, I can flip it and I still know what my delta H is. And that's going to be important when we get into playing around with Hess's Law. So a couple other important things. We can add chemical reactions together like a mathematical equation. So you've probably in some of your math classes added together multiple mathematical relationships, and you basically add everything on each side of the equal sign and can bring it down kind of together. So we can add these reactions. We eliminate terms that are in common on opposite sides. So if I had an X on both sides, if we're thinking about it in terms of math, then I could divide them out. I could combine like terms, so if I have a Y in a couple places on one side, then I can combine them together. And then by adding those together, we can find out new information about that kind of target reaction, the one that we're looking for. And we can do that through Hess's law of heat summation, which says, sort of as the name implies, that we can sum together, we can add together the heats of each step in a stepwise chemical process in order to find the heat of the overall net process or of the target reaction that we're looking for. We just need to find the right steps, and we need to manipulate the equation so that the steps look like the reaction that we're looking for. So let's do an example. If I have a question that looks like this, find delta H for this particular expression. So we have 2 carbons and an oxygen giving me 2 carbon monoxide, and I have these 2 steps to work with. Then I'm first going to say, well, this is my target reaction. This is what I'm trying to get to. And if these are the steps that I have, and I can use these because I have known delta H's here, then I need to figure out how does this get to this? What in this looks like what I'm trying to get to? And what in this looks like what I'm trying to get to? So I need to be able to kind of take a step back and recognize the pieces and parts that could come from each of these. And then when I add them together, hopefully they'll end up being my target. So if we look at this thing, we'd say, I need 2 carbons to react with 1 oxygen to give me 2 carbon monoxides. The only place that I see carbon here, if I'm just kind of looking for the unique thing, is in reaction 1. So I only have 1 of them though. So in order to get to 2, I bet a good place to start would be to multiply the whole thing by 2. So if I multiply this whole thing by 2, then I end up with 2 carbons, 2 oxygens, 2 carbon dioxides. And what happens is then I have 2 times my delta H, right? So when I multiply this times 2, my new delta H still has the same sign. I haven't done anything about flipping the equation or anything, but I multiply it by 2. So I have 787 kilojoules per mole. Okay? All right, so now I have 2 carbons, so that's good. I have too many oxygens here, but maybe I can sort that out because I have some oxygens here too, and I have 2 carbon dioxides. There are no carbon dioxides in this one, so I know that I'm going to have to get carbon dioxides on the reactant side of my other reaction when I add these 2 things together. So now if I'm looking at this one, I know I need to get carbon dioxides on the other side, and the other thing that I notice is I'm looking to make carbon monoxide. The only place that carbon monoxide is in the reactions that I'm given is right here on my reactant side. So I'm going to have to flip this thing around. So when I do that, it gives me 2 of my carbon dioxides on this side, which gives me 2 carbon monoxides and an oxygen. And what I do to my delta H then is to flip the sign. All right. Now when I look at these, so I've flipped this reaction and now I'm looking at this reaction and this reaction. If I add them together, so this is the Hess's law of heat summation, we are adding these things together, then I add everything together on my reactant side. So I have 2 carbons, 2 O2s, and then from here I have 2 carbon dioxides, and that gives me 2 carbon dioxides here, so I have everything on my product side now. 2 carbon monoxides and 1 O2. Okay, now we know that our next step is going to be to eliminate things that we have on both sides of the reaction. And so if I want to get rid of things that are in common, I could say, well, I have 2 carbon dioxides on this side, 2 carbon dioxides on this side. I have 2 O2s on this side, 1 O2 on this side. So if I get rid of one of these guys, I can get rid of one of those. So now I have 1 left over. And what this leaves me with is 2 carbons, 1 oxygen, giving me 2 carbon monoxides, which is very exciting. I just got to my target reaction, right? That's what I was looking for. That's what I got. Excellent. Now what it says is to find delta H. So now I have to say, well, I had this delta H when I rearranged that first one to get to this one. I have this delta H that I rearranged to get to this one. So Hess's law says I can sum these together. I add them together, and then I can get the final delta H for this process. So that delta H looks like I have a positive 566 and negative 787. I'm expecting this to be a negative number then, and I get 221 kilojoules per mole. So this process is exothermic. I wouldn't have been able to just get that number from these original numbers that I was given. I had to manipulate these reactions, I had to rearrange them, play around with them, do the same thing to the H values, the enthalpy values for the reaction, and then add them all together via Hess's law, and we can get to a final answer. So kind of fun. I like doing these problems. I think they're sort of cathartic. I think it's fun, like solving a logic puzzle.